All right, it's question show time. Your questions, my answers, wherever you are across our channel. If a question pops into your brain, just write it down. I will gather them up and I will answer them here. So again, we got a special guest answerer today, so stick around to the end of the show and I think you'll really enjoy it. All right, let's get into the questions. Disaster Arena. Could ion drive acceleration ever be so much to serve as artificial gravity for astronauts traveling within the solar system? You've been watching The Expanse, I think. This would be amazing, right? This idea that if you could just continuously accelerate a spacecraft at 9.8 meters per second, that would match the acceleration that we experience down here on Earth thanks to the gravity of the planet. And if you could keep doing that, just keep accelerating and keep accelerating, you would absolutely create artificial gravity that astronauts could walk around and they would be going faster and faster to their destination, and then they could turn around and slow themselves down at that same rate. It would be a perfect world. The problem is we have no way to create that much thrust from a spacecraft for any long period of time. We can get by for a few minutes, maybe using a chemical rocket. But as I mentioned in the video on ion engines, they provide as much thrust as if you hold a piece of paper. And that's like a full ion engine designed to push a spacecraft around the solar system. So there are more significant ion engines in the works that maybe could be hooked up to nuclear power plants and have much more energetic thrusts that are coming out the back, but it still won't be anywhere near what you would need to be able to have anything like artificial gravity. And we just don't have anything that would be able to do it. Unfortunately, it's going to be a while. If we get to a point where we have fusion drives that can be running for a long period of time, maybe we'll have a chance at it. But I think that for the longest time, producing artificial gravity through continuous acceleration is going to be in the realm of science fiction. I'm sorry. HL65536. Answer to question 1 isn't really correct. I believe that answer for a long time, and then I watched a lecture about the process to extract information out of the raw data from microwave background images. I was surprised to hear that the absolute speed of the Earth has to be taken into account to remove Doppler effects on the microwave radiation. No matter where you are in the universe, there is always an absolute point of reference, the CMB. Okay, so in last week's episode, I talked about how everything is relative. There's no perfect stop in space, that essentially you just always have to say compared to what, right? Are you stopped compared to the Earth? Are you stopped compared to a galaxy? Are you stopped compared to Jupiter? What is it going to be? And I had a bunch of people say, oh, well, an absolute point of reference is the cosmic microwave background, which is the leftover illumination from when the universe finally got transparent and light could escape into the universe. And that's just another thing, right? Like, absolutely, there's such a thing as the cosmic microwave background, and you're exactly right. When astronomers are working with the cosmic microwave background, they have to remove the Earth's motion around the sun, have to remove or account for the solar system's movement around the galaxy's movement within the local cluster, that there is an absolute speed that we are moving compared to the cosmic microwave background. But when you think about what the cosmic microwave background is, it is just this time when this light was able to escape into the universe. And everybody's cosmic microwave background is different, right? So if I'm, say, in Andromeda, the light that I'm seeing is different from the light that you're seeing. So am I stopped in respect to the cosmic microwave background from a person who's being inside the Milky Way, or am I being stopped from the perspective of someone who's being in Andromeda? It's just another thing to be relative to, and in fact, it is a purely subjective thing, right? When you are standing in a fog, and you can see near you very closely, and then far away, everything gets kind of fuzzy and foggy, and then you can't see anything more. That is a personal experience that only you're seeing from your perspective. Somebody else sees a completely different sphere around them in the fog. So I think that was great, and I should have mentioned that in the video, but that doesn't provide a definitive laws of the universe. This is a thing that is an absolute reference point. It's just another thing to be related to. Ido Deckers. Hey Fraser, is magnetic launch possible, cost-effective, something like the catapult on a new aircraft carrier, either to give initial velocity or less likely to orbit? I mean, you're talking about various kinds of kinetic launch vehicles. Think about like rail guns or Gauss guns, things that use electricity and magnets in some way to speed up a projectile to high velocities. And now I think apparently the Chinese have put one of these on one of their ships as a weapon that can be used, and it sounds pretty terrifying, and it's very effective. Could you use it as a rocket launch system? Probably. People have proposed this idea, launch loops, electromagnetic rail guns, things like this. There's a couple of problems with this. One is the amount of acceleration. You know, with the kind of railgun that you could use to accelerate a payload to orbital velocities, you need either something that can handle a lot of acceleration and have a very short launch track, or if you're going to launch human beings, you actually need a launch track that is 100+ kilometers long. Otherwise, you'll kill the passengers as you accelerate them. And you actually need to have your launch track built up this big slope, dozens of kilometers into the air, to make a smooth enough trajectory for you to be able to reach that orbital velocity. But I think your idea about use a head start, use some kind of, man, the birds are going crazy right above me. I apologize in advance for the bird sound. There must be some combination where you begin the acceleration with your electromagnetic system, and then a chemical rocket system takes over for the rest, and you get savings in the amount of fuel that you have to carry. The other problem is that a launch system like that, if you provide sort of your launch in one kick, right? It's this idea of could Superman kick a person into orbit? And no, because they would explode in the atmosphere by going that velocity. But the other part to it is that you can never get into orbit with one kick, right? So when a spacecraft launches, when a rocket launches, it goes up, reaches what's called apogee, which is sort of the height of the orbit that it wants to hit, and then it fires its rockets again to circularize its orbit. And if you've just got this one launch that's coming off of the ground and you're kicking yourself up into a high trajectory, you're going to return back to the Earth, or you're going to go into beyond escape velocity, and you're going to head off into the rest of the solar system. So I think we have sort of technological engineering challenges to make this work. We've got the issue that you're still going to need some other kind of booster to be able to circularize your orbit, but I think it's a good direction. And I know there's a couple of companies that are working on these ideas to try and figure out a way that you could do this over the long term. So stay tuned. And if cool projects are shown, I will definitely be covering them in the future. Olex. Hey Fraser, what if our electromagnetic spectrum is different from an extraterrestrial civilization? They would see other colors than us, something that we would never be able to see. Is that possible? The electromagnetic spectrum is the electromagnetic spectrum. It is one of the fundamental forces of the universe. Radio waves, microwaves, infrared, ultraviolet, visible light, ultraviolet, X-ray, and gamma rays. It is this single spectrum, and it is across the entire universe. We happen to have eyes that let us detect a certain region of the electromagnetic spectrum, from red to violet, and we can't see ultraviolet, we can't see infrared. And different animals have a different part of the spectrum that they're able to see, and even sort of more gradation. But at the end of the day, they're just perceiving the electromagnetic spectrum. So you could absolutely imagine some alien civilization using infrared to see or ultraviolet to see, but it's not a different electromagnetic spectrum. We would still be able to communicate with them, and they would be able to communicate with us. We just wouldn't necessarily be able to see with our own eyes what's being given off, but we could use our instruments to be able to detect them. I mean, that's what a radio telescope is. It's allowing us to see the electromagnetic spectrum at a region that our eyes can't see. While a telescope, we're seeing visible light in this, that is of the same spectrum that our eyes can see. So there's not like some different spectrum that aliens would see that we couldn't see, and so we could never communicate. It's just that we might need to use technology to be able to communicate with them. 420 Ninja. If we assume for a second that there is life on Europa, is it not possible that we could bring some back, sort of an alien pathogen with a sample return mission? Viruses, bacteria, and parasites are so dangerous because they evolved in lockstep with us to exploit our weaknesses, or to make more copies of themselves, or to, whatever they have evolved to do. And we have defenses, and our defenses evolve to try and withstand them. And it's this arms race that goes on and on. And so you would imagine if we went to some other, brought back a sample from Europa or something like that, that whatever creatures came from that place, they wouldn't have evolved with us in any similar way. And so we wouldn't anticipate that they would infect us in the same way that a virus or something can infect us here. Completely different evolutionary pathways. The likelihood is very low. The big risk, the thing that people are concerned about when you bring samples back to Earth, is that you don't want to contaminate it with Earth life. You want to know that the sample that you brought back, this weird alien creature from Europa, hasn't just been contaminated with an Earth bacteria that's really weird, and you have a confusing science result. And that's one of the reasons why scientists want to be so careful about how they bring this stuff back to Earth. Proud American Rob Man. Got a question. If we ever become a civilization that travels the solar system galaxy and starts to colonize it, is there any type of universal measurement for the time, like day, hours, minutes, that we can use so everyone's on the same clock? I assume 60-60-24 would not work out. When you think about it right now, our time system is totally arbitrary. I mean, there's no reason why you should break a day into 24 hours. It makes sense that you would break a year into 365 days because that's how long it takes for the Earth to turn once on its axis, right? A day. But there's no reason why you should break it up into 24 hours. There's no reason why you would break an hour into 60 minutes, and no reason why you would break a minute into 60 seconds. So because they are arbitrary already, I would assume that as we move out into the solar system and into the universe, we will just hang on to that arbitrary time scale and just keep using it. I can just imagine in the year 3000, year 5000, the computer, our robot overlords will still measure time in seconds or nanoseconds because it's what everything is coded in, and it's too much of a pain to come up with some different number, like the vibrations of a cesium atom. So yeah, I think in the far, far future, we'll still have the same time system. Fraser, TGB. There are 3 ways that we, the public, know of. Lockheed, Northrop, Boeing, Douglas, etc. certainly know of more ways. Lockheed has threatened to produce a small solar fusion reactor any day now. Why do you think Lockheed did that? Does anybody think that solar isotopes and fission are the only games? This was based on the episode that I did about power in space, how there's solar power, fission power, and radioisotopic generators, and that right now fusion is sort of outside of our reach. And sure, there could be technologies that have been developed that are more powerful than we are aware of, and they haven't been released to the general public. And so what, right? Like I'm not going to put one of those technologies in my spacecraft or Mars colony because it doesn't exist yet, and no one has told me. And then if someone tells us, then I'll use it, right? Like, sure, there could be all kinds of things that are being developed in secret, and then if they never tell anybody, then it's kind of like they never happened. And I think, we've heard that Lockheed Martin is planning a small fusion reactor. Great. Finish it. Lockheed, and share it with the public, and let's see it work, and people can do tests and implement it in their ships and spacecraft, and let's get going already. I think the fusion has been an incredibly difficult technology for us to master. And you see the Europeans with their ITER project, and the Chinese and Americans are racing to make a sustainable fusion plant work. And if one of them is able to do it, then they're going to have a method of almost unlimited power that will be relatively inexpensive. So there seems like a big incentive to roll these technologies out, and not a lot of incentive to keep this a secret. So, but yeah, Like, for sure, there could be all kinds of technologies we don't know about, and until they tell us, then it's as if they don't exist. And I don't even care. I'll wait till people tell me things that exist. Robert McPherson. If the Clipper lander missions to Europa confirm the presence of life, then what are potentially likely scenarios that would play out from a government budget and national science agenda perspective? Can we expect extremely rapid and substantially funded follow-up missions? Would it rally immense international cooperation, or would it result in competition from the likes of China and the US to make first discoveries? What would the major considerations that inform international policy and how we continue to probe Europa and disturb, interact with the life there? That is a great question. And I think that if there was like absolute certain life discovered on Europa, it would be everything that everyone was talking about for a short period of time. Then it would fall down a news cycle, and sites like us, we'd keep talking about it, but most people wouldn't be that excited about it. You would see a tremendous amount of prioritization in sending follow-up missions to map out the scale and the size and the kind of life that's there. And you might see a follow-on Europa mission and a drill mission and all these kinds of things. But I don't think it would have the kind of sort of deep existential crisis collaboration that a lot of people think would happen. Like, huge chunks of the ocean haven't been explored. And we find all kinds of interesting life in the middle of really extreme biospheres in Costa Rica and places like that. And so for us to find unusual life is not a thing that is completely out of the bounds of what we've seen before. It would be alien life, probably, right? Or connected through some kind of panspermia event. But I think you would be amazed at how quickly human beings can kind of internalize and become numb. I don't know if numb's the right word, but bored with an amazing new mind-shattering discovery. And so you would see increased budgets in Europa missions, and the news and the science would trickle back. I don't know if there would necessarily be a race. There might be more cooperation, but it would just be, and then people would be looking for, like, does Enceladus have the same kind of life? When did it differ from us? So I don't feel like it would be the kind of enormous, world-changing, society-changing event that we would hope that it would be. And you can have this sort of glimmer, the sneak peek of it remember back in the 1980s when they announced that they'd found life on Mars, those little wormies in a meteorite, and there was a lot of news, and then there was an argument, and people kind of maybe debunked it, and it's still a controversy. That was the discovery of life on Mars, and here we are, and we barely talk about it, right? Was it really life? We don't know. And so I think that's the problem, and that's what we will see for a long time. And by the time we do understand exactly what it is, people will be bored, and we'll just sort of deal with that on our regular, ongoing, day-to-day lives. Marty Ninja. What is the Milky Way orbiting? The Milky Way is actually part of this region called the local group. So there's 3 big galaxies in the local group. There's the Milky Way, there's Andromeda, and there's Triangulum Galaxy, M33. And then there's a whole bunch of smaller dwarf galaxies that are caught up in this mix. And those 3 galaxies are orbiting the common center of gravity of the local group. And they're all sort of spinning around this region. And the local group is part of the larger Virgo supercluster. And same thing, all of the galaxies and all of the galaxy clusters are all orbiting around this common center of gravity. And the Virgo supercluster is part of the Laniakea supercluster. Although after a certain point, as dark energy and as the expansion of the universe is a stronger force than the gravity that's pulling these things together, it doesn't really make sense to say that they're orbiting anything. But yeah, so the local group, the Milky Way, and the rest of the galaxies in the local group are orbiting the common center of gravity of the local group. S47. How does one dispose of heat in space, and what kind of processes are used in satellites? There are 3 ways that you can transfer heat. There's convection, where you've got like particles of air that push, warm air. When you feel a warm wind, then you're experiencing convection. You've got conduction, where, say, a metal can transfer heat, where the molecules are bumping into each other and transferring heat along. And then you've got radiation, where essentially photons of radiation are emitted by something and it cools down in its temperature. And out in space, you can't use those first two. You can only use radiation. And it's actually a pretty big problem. You can have a spacecraft be getting a lot of heat from the sun, for example, and not able to get rid of that heat. And so the best example, and I hope we can sort of have a picture of this, is on the International Space Station, there are radiators. And what they do is they take ammonia and they pump it through these radiators because it is able to convect the heat out into these radiators, and then the radiators radiate the heat away from the International Space Station. And they're designed to be the right size to be able to let the space station get rid of the heat that it is absorbing from the sun. And when you think about how much time it spends in sunlight and how much time it spends in shadow, and you see they're actually really big. Like when you look at the space station, it looks like they are other solar panels, but they're not. They're radiators designed to get rid of all that heat. And any spacecraft design needs to take this into account to make sure that it doesn't overheat when it's spending time, especially close to the sun. So radiators, savannas. Fraser, I can't figure this out. My experience in Kerbal Space Program has taught me that a higher orbit has a lower orbital speed. However, I cannot explain this to anyone, as I can't find the logic in it either. Is it that the decreased gravity due to distance? Is it the centrifugal force increases with radius? Or does that even exist in orbiting bodies? Please explain this to me. No problem. So when you think about gravity, right? When you think about orbits, let's start with orbits. So when you think about orbits, you've got you're in balance. As you are orbiting, say, Earth, you have all the forces around you are in perfect balance. And so you don't experience an acceleration in any direction. You're going around and around the Earth. Now, what are the forces that are working on you, right? You've got the force of gravity that is pulling you down, and that's counteracted by your orbital velocity, your momentum as you're going around the Earth. That is, that gives you a force that is pushing you outward. And those two forces are in perfect balance. And so you don't crash into the Earth and you don't fly off into space. Now, the force of gravity drops as you go farther and farther away from the object that is pulling you down. So if you go twice as far away from the Earth, then you're going to experience less gravity, right? Is it half? Inverse square law? I think it's the inverse square law. You're going to experience half the gravity, a quarter of the gravity. Anyway, I apologize in advance. You experience less gravity. And so you've got, when you think about those two forces that are pulling on you, the one that's pulling you towards the Earth is now a smaller number. And so therefore, to counteract that smaller number, you have to be going less quickly. You have to be going more slowly. You have to be generating less of that outward force from your velocity around the planet. And so at every point, the closer you get to the planet, the faster you have to go to counteract that gravity. The farther away from the planet you are, the slower you have to go to counteract that gravity. And that's how it works. And it is a very counterintuitive thing. You would expect that the farther away you are, the faster you have to go because it's like a bigger distance that you have to go around the orbit. But no, it works the other way around. Tim Robinson. How do astronomers judge the speed of galaxies, objects, etc. when everything is relative? They often say a galaxy is moving away at a certain speed. Is it as simple as that speed is being measured in relation to Earth? That's a great question, and I have called in a friend, Athena Brensberger from Astroathens YouTube channel, and she has a great Instagram channel, and she does really great explainers, goes into the math a lot of the times in some of these kinds of questions, and I thought I'd let her tackle this. So watch her answer now.
Hello everyone, Athena here from the Astroathens channel. So I got this really great question about how astronomers are able to measure the speeds in which galaxies are moving and also other objects in our universe are moving when everything in the universe is supposed to be relative. Very valid question. He actually follows up to say, is it because we are measuring the speeds of these galaxies and objects in respect to Earth? And the answer to that is yes. We are measuring the distances and the speeds in which galaxies and other objects in our universe are moving based on Earth using something known as Hubble's law. So Hubble's law pretty much says that the velocity of an object is directly proportional to the distance of the object. So one thing that's actually used is something known as the Doppler shift and also the red shift of the galaxies to measure where it's actually moving, redshift, blue shift. I'll explain that in a second. So every object in our universe either emits light or reflects light, other than dark matter and dark energy. We're not going to talk about that right now. But everything as far as matter goes that we're able to actually see, so luminous matter, like stars and galaxies, other objects that are moving, all of them give off a light spectrum, right? So they're able to give off some bright light, like Earth reflects the light from the sun. Other stars are able to emit light, and galaxies are made up of millions and billions of stars. So we're able to visually see that. Now, based on their light spectrum that's actually picked up, we are able to measure, astronomers are able to measure the distances based on that light spectrum. And what was found is that all galaxies are moving into the red shift of what I was bringing up before, of the Doppler shift. What I mean by that is if you have something moving close to you, like a car, for instance, we like to do this a lot in physics class, is explain the Doppler shift by a moving vehicle, because it doesn't just work by light, it also works by sound waves. When something is moving close to you, it's getting higher and louder and higher pitch. The frequency is getting more like this, and the wavelength is getting more crushed. That's blue shift. So it goes woo as it's moving further away. That the wavelength of its sound wave is actually stretching, and that's becoming something known as redshift. Galaxies are doing this. Their light that we are picking up is red shifting away from us, meaning we are measuring now that it is moving away. That's kind of a general explanation of how we're able to measure that everything is moving away from us in respect to just the expansion rate of the universe. And this is actually how the expansion rate of the universe was measured. As far as specifically the speeds go, if they're able to actually break down the rate in which this redshift is moving, that's where the speeds will then come in. That's how, based on the wavelength of light and how much it is red shifting, so how much it's stretching and getting longer and longer and moving further away, the light is getting more stretched out by its red shift, is how we're able to actually measure the speed in which it's moving. So as far as like what I was saying, let me try to draw this out for you guys to re-explain it. Pretty much you have like Earth, we'll just say, okay, here's planet Earth.